and Quicksort. So these are both theta n log n sorting algorithms. So we've already seen another theta n log n sorting algorithm, which is what's the sorting algorithm that we've already seen in this class? Yeah, heap sort, right? So heap sort also does n log n, but what's more common are Mergesort and Quicksort. Both of these algorithms are examples of a paradigm called divide and conquer. So you'll learn a lot more about divide and conquer in 102, but I just want to give you the basic sort of paradigm for divide and conquer. It's a method for faster algorithms using recursion. So the way it works is, given a problem, and it's easiest to think about especially a problem where the input is an array, right? So like sorting. So what you do is you first divide into subproblems. You solve each recursively, and you conquer, which is the sort of conquer step, by putting solutions for subproblems, or I should say, instead of putting, I should say by combining is a more appropriate word. Combining solution for subproblems into the solution for the whole problem. And the nice thing is, you only have to figure out step 3. Meaning, sorry, let me zoom out. The idea is, if you can find out a way, like if you can find out a little piece of code or an algorithm that can combine solutions to subproblems, then if you use the divide and conquer paradigm, you will automatically have a solution for the whole problem. And the best example of this is Mergesort. So I'll show you what I mean by this. So the idea is that instead of trying to figure out how to solve the whole problem, if you can just figure out how to combine solutions for subproblems, which is often easier to do, it's easier to think about, divide and conquer will give you a way of just converting that to a whole solution. Okay, and the classic example, and probably the best example of this, is Mergesort. You also have to kind of figure out how to divide into subproblems, but often that part is easier. So what we have is sorting an array of ints of length n, right? So here's my array A. So how could I divide it into subproblems? Well, I could just divide it into two halves, which I'll call L and R, which are the left half and the right half. The left half and the right half. Okay? Suppose L and R are sorted recursively. Now, often this is very confusing because you can say, but I haven't figured out how to sort, like, what does that even mean? I don't even have a sorting algorithm. And this is again where, sort of, you may have seen this in the n-queens problem, that when you do the recursion, you're like, but how am I going to call it recursively if I don't even know how to solve it? But somehow, if you just place one queen, the recursion kind of takes care of everything. I don't know if that makes sense, right? So there's something similar over here, except it's a different viewpoint. So the idea is, Suppose these were already sorted, meaning that L was sorted and R was sorted. Suppose magically you could assume that, then how to sort A, which is L union R? By the way, that U is not it's not a U, it's the cup, it's union, right? This is the union operator. So this is the problem of merging sorted arrays. Okay, so if I have two sorted arrays, so I have, here's L, which is sorted, and here R, which is sorted. Okay? Suppose if these are already sorted, can you find out the sorted order of everything quickly or easily? Right? So what is the first thing that you would do? You would say, okay, let's find the minimum element in the whole thing, because that will be at the beginning of the sorted order, right? So what is the minimum element in this? How do you find the minimum element? Yeah? Exactly. So it's the minimum of the, and because we're counting from 0, like the 0th element of L and the 0th of R, right? The beginnings, so the beginning, the minimum of these elements, that's the overall minimum. Okay? So suppose this was the minimum. Suppose that was the minimum. Then what's the next element in sorted order? Yeah? Somebody else? Yes?
Like the first element of L.
This one?
Yeah. Or like the next one?
So, okay, so let's just say that I'm going to write, this is going to be sorted A. Right? And so I know that this element is going to go there. Right? Because it's the minimum of both. The question is, what is the next element? Does the question make sense? So the next element always going to be that? Yeah? So it's either this or this. Right? Because L could have been something like 42, 100, and the first element here could have been 101. So it's actually going to be the minimum of these two elements. Right? So it's the min of these two, which you would then move here. Then the next one is going to be the min of these two. So maybe it happens to be this one. That goes there. So on and so forth. Right? So there's the idea, and this idea comes up a lot in many solutions, is this idea of what I call marching pointers. You have one pointer in L, one pointer in R, and they're just going to sort of march through the array with some operation. Right? And this idea will be there, is so useful in solving so many different problems. Does this make sense, the logic? Yeah.
So like it's called merge sort because like you're kind of trying to combine everything together at once when you go back and forth.
It's called merge sort because the operation of combining sorted arrays is called merging. So the main operation here is how do you sort two arrays that are already sorted. Like the left half and the right half are already sorted, so this is called merge. Like this operation is called merge, and that's why it's called merge sort. So let me write out sort of the basic pseudocode for merging. I'm going to write it sort of in English so that, I don't want to deal with explicit, whatever. I don't want to deal with like syntax issues specifically, but I'll just say that, so we'll initialize IL, which is an index L, and index R to be 0. So I'm using somewhat mathematical notation here. And so we'll initialize an output array A of length, the length of L plus the length of R. Right? That's just going to be the output. So your function here It's just I give you two sorted arrays, output the sort of everything. Okay? So the third step is while, okay, now I'm going to have to write some condition here, and we'll come back to this condition in a bit. So we'll compare L of IL and R of IR. And store the min at A. Okay, so I'm also going to have a new index that I'll call I of A, the index of A. Okay? Then I'm going to increment IA. And then what I do is I increment IL or IR depending on which of LIL and RIR was smaller. And if they're equal, you can break ties arbitrarily, so I'm not going to worry about that. So does this pseudocode make sense? Right? There are 3 pointers in here, right? There's one pointer called IL. There's one pointer in IR, and there's some pointer IA. Pointer, index, whatever you want to call it. We compare these two elements, put the minimum over here, increment IA, and then increment either IL or IR depending on which was the minimum. Right? So this is the merge procedure. Is this clear? So what is this condition? How long will it run? Yeah?
I just had a question if this would work on arrays of different sizes.
Okay. That depends on the condition. Yeah? Exactly. It's going to keep running until it one of these IL or IR hits the end. And then what happens? Yeah? Then you just copy whatever is left, right? So if IL finishes and IR still has elements left, all of these elements must be more than the elements in L. So you just copy all of that to the end. Does that make sense? Right? So often a convenient way this is done is you could imagine that you stick an extra element in here that's infinity. And that way whenever you compare something with infinity, it's always smaller. And you can do that. You can do this in many different ways, right? Whatever is convenient. So when you code this up, you need to write out what the while condition is. You can do this in many ways, but basically the while condition is while we have not reached the end of L or R. This is a little, while we have not reached, no, this is badly wrong. While we have not reached the end of L and not reached the end of R. Okay, that's the while condition. But this over here, this is the basic pseudocode of merging two sorted arrays. It's quite like, I mean, again, the best test that you understand it is to code it up yourself, but you'll see that the logic is not very difficult, right? So it's just essentially the way to think about it is you have 3 pointers, IL, IR, and IA. And IA is actually not that important. That's just going to sort of march through. But all these pointers are just always going to be incremented. Okay? Okay, so this is merge. So just to a little bit of understanding, here's a question. Given L and R sorted of length n, what is the running time of merge L and R? So I'm calling this function merge L and R, right? This function that I've written here, this method that I've written here is merge L and R. Question is, what is the running time of merge L and R? Is it essentially theta of n? Is it theta of n log n? Or is it theta of n squared? I'll give you a few minutes to decide what the answer is. What is the running time of this algorithm here? Question?
Why is the law condition and not or? Because when you want to break the law loop once you reach the end of one, and then dump it.
Exactly. So if you think about, we have not reached the end of L and we have not reached the end of R. De Morgan's law. You can do an or if you do not of this or that. Okay, yeah, so what's the answer? What's the answer? Okay, there's, I see all colors here, right? So there's some blue, there's some red, there is some green, there's someone showed a green and then I think took it away. Okay, all right. So before I tell you what the answer is, why? What is the logic behind that? Yeah, in the back, yes. So what do you think the answer is? Okay. Okay, all right. So that was the reasoning. Yeah.
Because we're using the marching pointers, we only see each element once. So adding another one would only increase it by one.
Okay, so because the pointers are marching, always incrementing, you see each element once. Anyone who thought it was something else? No? Yeah? Theta of n log n. I did. But this is not merge sort, this is merge. Yeah, okay, so I think, I don't know, I'm convinced by the most recent argument, right? Every element is seen only once. Because if you look at these pointers, which is also what was said earlier, these pointers are sort of marching, they're incrementing. So this pointer is going to increment, this pointer is going to increment. In every iteration of the while loop, one of these pointers is going to move up. That's what is important. In every iteration, one of these pointers is going to change. This is not a nested double for loop. It's like a combined for loop on both of them, which is a little more confusing. Right? So it's right. The answer is theta of n. There are multiple ways of seeing this. Here's another one, is if you look at this while loop, in each iteration, IA is incremented. And obviously, IA can only increment 2n times. Right? In each loop, this pointer, IA, is incrementing. how many times can it increment? At most the length of A, which is 2 times n. So this while loop is going to run only for 2 times n steps at most. Is that clear? Right? So it's not like insertion sort or selection sort or bubble sort or these other sorts where there's double nested for loops. There's only one while loop. And each time the while loop runs, each time this loop runs, IA is incremented. That's one argument. Or you can also say that either IL or IR is incremented. Both of them are not going to increment in each step, but one of them always will. So the argument is each iteration of the while loop increments IA. This is equivalent to saying that it adds a new element to the output A. There are at most 2 times n increments of IA. The while loop runs O of n times. So the whole running time is O of n, right? Because all of these parts, these are basically constant time. Right? Is this logic clear? Right, so this is a very important fact, which I'm going to write down sort of separately. Given L and R of lengths M and N respectively, this is just saying that the length of L is M and the length of R is N, given of length both sorted, merging can be done in theta of M plus N step, whatever, let's say running time. This you need to remember, right? This is like a really important fact. Given 2 sorted arrays of length M and N, you can essentially merge them in linear time. Okay, this is a really fundamental fact for you to know, right? And it's a very useful one. Lots of questions that someone says, oh, how are you going to do this? The answer is often you'll find 2 sorted arrays and you merge them, right? Merging is a really efficient operation as well. It's also space efficient. All it maintains are these 3 pointers. Okay? So that's what merging means, merging sorted arrays. Usually when they say merge without, it often means merging sorted arrays, which is to combine 2 sorted arrays, right? Any questions about that? Is that clear? Okay, so again, I'll repeat, you must know this fact. Okay? Remember this, and to see why this is possible, there's that pseudocode that I've written there, which is not particularly complicated, but go back and look at this, but make sure that you remember this. I don't want you to be caught somewhere where someone says, how long does it take to merge? And like, oh, I don't know. It's merging, it's 2 sorted arrays, linear time, always. Right? Very important. Okay. Now, once you have the merge procedure, merge sort essentially writes itself using the divide and conquer paradigm. Okay, so this part often can throw you off. So let me write this as merge sort of an array A. So the base case is that if the length of A is at most 1, so either it's an empty array or it has length 1, we will just return A. There is your base case, right? So you set the array L to be A from 0 going to n over 2, and R being n over 2 plus 1 going up to n minus 1. Again, you can take floors or ceilings or whatever, but you just be consistent. Right? So this gives you the left half and the right half. Here is A, and that's L, and that is R. What you do is you call merge sort of L, merge sort of R, and then finally you just output the merge. Well, okay, let me write this as L is equal to the merge sort of L, R is equal to the merge sort of R, meaning that I'm just going to reset L to be the sorted version, reset R to be the sorted version. I'm just going to output the merge of L and R. Okay? So these were the divide steps, and that is the conquer step. And that's the code for merge sort. Like once you write the code for merge, you have this function, then this is all you need. So it's surprisingly short once you figure it out. But you have to think a little carefully about how it works. Right? The way to think about it again is through recursion, right? Recursively, you assume that L and R are going to be sorted, and as long as this merge is going to be correct, then the whole thing is going to be correct, and so that gives you the code for merge sort. Right? Any questions? It's not obvious why this runs in n log n time. That's something I will come to later. But right now I want to make sure that this you understand, that you can merge in linear time. And once you can merge in linear time, at least you can write that procedure down. Yes?
By step number 5, output merge, does that mean like return the merged array L and R back to like one of the merges in step 3 and 4?
Well, I'm just thinking. Okay, so I'm being a little maybe not so careful about the memory. So I'm just saying that imagine that the merge procedure as written here, right? You give it L and R and just initializes this new output array, and so it just returns that whole array. So I should have probably said over here, like step 4 would have been return A, like when all of this is done, right? So step 4 is like return A. So it's going to return the merged array. So usually the merge operation, okay, this is an important point, but somewhat technical, is that the merge operation allocates new memory. So you can think of it as, it's like I'm just allocating some fresh memory here, and whatever is being returned, I'm just going to copy that to L. So, yeah. Usually the memory would then get freed as it goes back up, right? So I'm not being careful about my memory management here, because I just want to explain the basic logic. But yeah. But this is an issue with merge sort, that it actually requires fresh memory because it's doing the merge step. Okay? Yes?
Can you go into a little more detail what you exactly mean by output, merge, LR?
Okay. So I could do that. Thank you. Sorry. Return. Thanks. Yeah, I should have said return, not output. Yeah? Question? Yeah, that's true. Usually you would do that. If you're really optimizing it, once the array is below a particular size, you just do insertion sort. But again, I consider that, so at some point one gets into like, the design of the algorithm and then the engineering of the algorithm. And a lot of what you're talking about is the engineering of the algorithm. because the overall runtime is not going to be affected. Like the big O runtime is going to stay the same whether you do that or not. So, right? So that's when you're trying to sort of shave off the constant factor in the n log n. Okay. So why this is n log n is that's trickier. I will get to that maybe, in a while. But for now, I want to make sure that there are no confusions about merge sort. And to me, in some sense, even more important than merge sort is you understand the merge procedure, because this thing comes up a lot. Like there are lots of different questions where, again, like if you should always think, can I use the merge algorithm some way? Okay. All right. Any questions about that? Okay. So what I want to do now is I will come back to the running time of merge sort after I tell you quicksort, because then we can put them side by side, and then we can talk about them together in terms of runtimes. Okay? So this is merge sort. So as was just discussed, merge sort, let's talk now about quicksort. So merge sort requires extra memory. Right? And this is exactly the point that was raised. And the reason that it requires extra memory is, let's go back to the merge sort procedures. So imagine that you're calling this. L and R you don't really need to reallocate, right? You can just take whatever array you have, and then you could basically say, okay, I'm just going to put a pointer to get L and R. But at some point, you have to call the merge operation. And when you call the merge operation, it initializes a fresh array and then copies everything using this mechanism, right? So the merge operation allocates more memory. So this is allocating extra memory, the merge operation. And that allocation is happening right here when I say initialize the output array. Okay? So more memory is being used. And so the technical term that is used for describing that is that merge sort is not in place. So in place sorting means that, okay, I'm going to write something here which may be a little confusing, but then I'll explain it. It requires only O of log n extra memory, not extra linear memory. So the way to think about it is, if the O of log n is confusing you, the way to think about it is it's only allocating extra indices, and then there's a log n extra memory because it's doing some recursion. So sometimes the recursion stack is going to start adding up. But it's never going to allocate a fresh array. Okay? So again, if the log n is confusing, you just think of it as the log n is just coming from some recursion. Because when you do recursion, there's a stack that has to be generated, and that's actually some memory that has to be allocated. So in-place sorting only requires log n extra memory. So an example of in-place sorting is heap sort. If you think about heap sort never allocates extra memory. Because once it builds the heap, it just keeps swapping within the memory that it has. It does the sink and swim operations, right? So heap sort is actually in place. Again, something important to remember. Heap sort is in place. Insertion sort, selection sort are all in place because they never use extra memory. They're just manipulating indices. Merge sort is not in place. That's one of the reasons why at like industrial scale you wouldn't use merge sort, because if you have to sort a terabyte of data, which many companies have to do all the time, you don't want to have another terabyte of memory that needs to be allocated to sort that 1 terabyte. Right? Because if you want to merge, then you're going to have to allocate new memory. And so in-place sorting is what you want. So there is an n log n in-place sorting algorithm, heap sort. And we'll also discuss quicksort, which is also n log n in place. Okay? So how does quicksort work? The way to think about quicksort is, again, it's divide and conquer. It's about dividing the array into 2 parts and then doing recursion. So the way you did it in merge sort was you split left half and right half, and then you sorted each separately. Quicksort is going to do it a little differently. What it's going to do is first looks at an element A0. It's going to pick what is called a pivot element, and the pivot is often just A0. It doesn't matter. It can be anything, but it picks A0. Then it's going to do something which is another important procedure you need to know called partition. And it's going to partition A by the pivot. So what that means is it's going to rearrange the array such that the pivot is going to be here, everything here is less than the pivot, and everything to the right is more than the pivot. Let's just assume that all elements are distinct, okay, just to keep things easy. And then you get your L and R over here, and then it's recursively sort L and recursively sort R. So again, I want to sort of contrast. So this is quicksort here. Now I have to tell you how to partition, but this procedure is quicksort, right? So the difference between merge sort and quicksort is, if you think about it, the divide step here is kind of trivial. It's just breaking it into 2 parts and doing recursion on each. Here, the division itself is more complicated. But note that once you rearrange in this way, then if you recursively sort everything in L and R, the whole thing becomes sorted. Does that make sense? Like, you've broken it up into 2 piles where L is going to be less than everything in R. So then you can just sort L and sort R independently. Does that make sense? Questions? Is everything clear? Yes? So say that again? Yeah, so you have to rearrange the array to get that. Okay. That's what partition means.
Yeah. Wait. So is partition sorting? Like, how do we know that what's in the left is less?
You don't. So actually, so think of it as initially the array is not going to look like this. But what you're going to do is you're going to swap a bunch of elements around so that it looks like this. And that is called partitioning. Yeah, it's kind of like, think of it as it's like, I don't know. I mean, it's sort of a natural thing when you want to sort cards or you sort something, right? You basically say, like, everything less than something, put it in one pile. Everything more, you put it in another pile. So then you have 2 separate piles, which you can then do separately. So partitioning is a procedure, just like merge is a procedure. So merge sort, the core of merge sort is merging and then recursion on top of it. Quicksort is partitioning and then recursion on top of it. But the core procedure is partitioning. So I have to tell you how to partition. But once I tell you how to partition, you could just use this paradigm here, which is you pick a pivot, the first element. You'll see that it doesn't really matter what the pivot is, at least in terms of the algorithm being correct, right? No matter what pivot you get, okay, so maybe if the pivot was down here, then L would be more than R, but that doesn't, but it's still going to be correct in the end, There's no issue with correctness. It's usually with running time that the pivot is important. Does this make sense? Okay. So now the natural question is how to partition. How to partition an array. Right? So let's just think of what the inputs to the partition method are. Usually you have an array A and you have a pivot. So you have A and you have some element pivot, which may or may not be in A. In this case, it's always in A. It's usually conventionally like the first element or the 0th element of A, but otherwise it's just some element. And what you want to do is you want to rearrange so that the pivot is here, everything less than the pivot is here, and everything more than the pivot is here. And for now, we'll just keep life easy and assume that the pivot is the 0th element. Okay, but in general, it doesn't matter. What is the simplest solution? Forget in place or allocate as much memory as you want. Give me a really simple algorithm that can partition. Maybe actually, you know what? I'm going to give you a few minutes to think about it. I claim that there's a very easy linear time algorithm that can partition. You are welcome to allocate more memory. The only thing is, given an array and an element, I want you to output an array of this kind, where you've rearranged everything in A so that everything less than the pivot is first, then there's the pivot, and then everything more than the pivot. I'll give you a few minutes to think about it, and you can talk or whatever to help you. The solution is really simple, by the way. It's single for loop. So think about it. Giving you a hint. It's a single for loop. It's not complicated, or maybe 2 for loops. It's really easy. Don't think complicated. Okay, so what? So who? Do you have it? Yeah. Don't link list. No. Why? Simple. Allocate another array. It's really easy. Yeah. Even simpler. Yeah.
Create an array, put everything that's lower than it into that array, and then if you want to make another array, if everything bigger goes in there.
That's it. Right? Yeah, you were saying something.
You could just make another array of the same size, and then just have like a pointer at the beginning of the array and a pointer at the end, and you just loop over it. If it's less than, you stick it at the beginning and increment that pointer. If it's greater than, you stick it at the end and decrement that
Yes.
pointer.
Yeah. So you're even doing something that is more like, yeah. So if you take your idea, we'll get to the more efficient partitioning. But essentially, yeah, you just allocate another fresh array, copy everything that's less than it in that array, then allocate another fresh array, copy everything that's more than it, and then you just put the arrays together. Right? Simple solution, right? Don't think complicated. No linked list, no binary search trees. You don't have to build an AVL tree, and then that's the way that you always work. Like, let's build a hash map and this, and let me do all this complicated stuff. No, just for loops, right? Right? So simple, but it's not in place because I'm allocating more memory. solution is create 2 new arrays, copy everything less than pivot in A to the first array, then copy everything more than the pivot to the second array. Right? So once we have this, we'll have everything less than the pivot here and everything more than the pivot here. And then put it together in one array and return, right? In a single array. And return. By the way, this is sort of, I mean, as an aside here, but an important aside, for all algorithms questions that you get, every single question, you can always solve it with just using arrays. It's just a question of efficiency. You can always solve any question using arrays and copying things over and over again. Everything. Right? And most students will ignore that solution, try to do something complicated. So this is then we can improve this. But first, get the simplest solution, and then we can start improving. So is this clear? Right? So this is just O of n time. Right? In this case, it's 3 for loops. And that's because I'm being really, really stupid here. Like I'm doing it in 3 for loops. But it's O of n. It's fine. It doesn't matter. Okay? Is this clear? Okay, so the running time is O of n. Which, if you think about it, you're not going to beat anyway. There's no way you're going to do anything less than linear time. Now, the problem is, in this whole discussion, we said we don't want to allocate more memory. That was the point of Quicksort, and our partitioning is allocating more memory. So what we want to now do is to partition in place, meaning partition without allocating more memory. Okay? Partitioning in place. Now this requires a little bit of cleverness. It's similar to using 2 pointers. Yeah, you want to So the way to think about this is, again, this is like marching pointers, but of a different style. So we'll have 2 pointers here. We'll have a pointer called head and a pointer called tail. Head is at the beginning, tail is at the end. Okay? So if head is less than the pivot, yeah, you want to say something? No. If head is less than the pivot, what should you do? I think you already know what the solution is. So if head is less than the pivot, what should you do? Yeah. Leave it there, right? Because it's where it's supposed to be. And if tail is more than the pivot, you leave it there. So what does it mean to leave it there? Increment head. I'll write this down, but let me first verbally say the logic, and then I'll write it down. If head is more than the pivot, increment head. I'm sorry, the other way around. That's what I was thinking of. If head is less than the pivot, increment head. If the tail is more than the pivot, decrement the tail. Right? So this is going to keep incrementing until it ends up here. And this is going to keep decrementing until it ends up here. When this pointer is stopped, what do you know? You know that A of head is greater than the pivot. And this pointer has stopped moving. A of tail is less than the pivot, right? So then you have this problem. Easy fix, you swap them. So you swap it and then continue. So we can swap them. So you basically just swap these two. And continue. So I'll write down the pseudocode over here, but hopefully the idea makes sense. So you just have these 2 pointers. One starts at the beginning, one starts at the end, and they will just come, and once they bump into each other, they're done, right? So this is called in-place partitioning. And yes. So for now, let's assume all values are distinct. What you can often do is, so let me say this one way. So one thing you can do is you can say if the head is ever equal to the pivot, it moves, but the tail always has to be strictly greater than the pivot to move. Like you break ties either with the head or the tail, right? You break ties consistently one way or the other. Or what is often done is the pivot is the 0th element. So start the procedure from element number 1, assuming all elements are distinct, and then you basically can at the end like swap the pivot to the right position. Okay? So I'll write this down, and it should be fairly clear. Yes. So if everything from the tail is greater than the pivot,
And the head was waiting for the tail to stop as well, to swap.
so the thing is, if none of the pointers ever stops,
What if just one of them did?
okay, so let's do that. So what is the situation you're describing? The tail does not stop. So if the tail never stopped, what this means is that everything in here is greater than the pivot, which means you're done already, right? If everything is more than the pivot, there's nothing to do. So if it ever stops, it must have stopped at something that is less than the pivot. Does that make sense? Yeah. Yes? No, so you should think of the pivot as just some value that you're pivoting, you're partitioning with. Conventionally, it's A0. Conventionally, it's A0. Okay? So let me write down the procedure here. So I'll say partition. So I'm partitioning A. Okay, so with some pivot value. And so what I'm going to do is let me make sure that I do the following. When I finish, everything less than the pivot is going to be here. The pivot is there. And everything greater than the pivot is there. And let's just suppose the pivot is A0. Right? So initially, the pivot is here. And we want this to become like that. I'm sorry? Yes, it can. Eventually, that's how you do randomized quicksort. You pick the pivot randomly. But it's always convenient to, whenever you pick the pivot, to make it the first element of whatever you start with. And then you'll see that the code becomes easier to write. So let me initialize the head to be 1. And the tail to be whatever the length is, -1. So I'll write it this way. So while head is less than the tail. So I'll say while the element at the head is less than the pivot. Again, I'm assuming all elements are distinct here, just to keep things easy. We'll do head plus plus. While A of the tail is greater than the pivot, I'll do tail minus minus, right? So I keep incrementing the head as long as it's less than the pivot. I keep decrementing the tail as long as it's greater than the pivot. And when they stop somewhere, I have to swap the elements. So I'll just swap A head with A tail. So swapping, I'm swapping the content. I'm not swapping the values of head and tail. Head and tail are indices. They stay where they are. I'm just swapping the content, swapping A head with A tail. Does that make sense? And so you keep doing this. So when you end, head is equal to tail. And then there's one step that's left. Step 3. One operation that's left. Sorry? To place the pivot, right? And where would you place the pivot? Exactly where this stopped. So then what you do is finally, okay, so this, let's be a little careful. Okay, let me let me write something and then we'll see if this is correct. Because I think I may have made a mistake here. We'll swap A0 with A of head. Is this going to be correct or not? Yeah. Only if the place you landed on was less than the pivot. Exactly. So this makes sense. So you have A0 here. The head is equal to tail over here. And so you want to swap A0 with this element. Although you're not sure if this element is less than the pivot or more than the pivot. If it's less than the pivot, then you should swap. But if it was more than the pivot, then what? Yeah? You decrement head and then swap. Right? So I'll say with this or A of head minus 1. You know, depending on if A head is less than the pivot. So I'm deliberately writing my code somewhat imprecisely because my hope is that you will go and then figure out what it is. Again, it's the logic that's important here. You're now hopefully at the stage where you can convert this stuff to code. Yes?
So if you always pick A0 as your pivot, and A0 happens to be the smallest element,
Right?
would that be an infinite loop then?
It's not an infinite loop because this loop will always end. You'll just end up with the same array as you started off with.
But if you were partitioning for the sort, it would always partition the same way.
Yeah, so what happened is you would partition the same, exactly. I mean, indeed, if you think about it, if you look at Quicksort, the worst performance of Quicksort is oddly enough when the array is already sorted. Then it actually takes the most time. Okay? Okay, so this is partition. And partition runs in O of n, or whatever, theta of n time. So this is, again, sort of very important. Just like you have the merge procedure, you have the partition procedures. These two procedures are important to know and understand well. Nobody's going to expect that you know how quicksort, the runtime of quicksort analysis. Like, that's complicated. The runtime of merge sort analysis, you should see it, but it's not that important that you remember it. But merge and partition, you better know, right? And they're both, the logic is both, in some sense, there's this analogy, right? It's all about 2 or 3 pointers that are marching through arrays. In this case, the head always increments and the tail always decrements. In the merge case, both those pointers always incremented. Yes? No. No. You don't care about those pointers themselves. Yeah. Okay, so let's take a short break now. And then after the break, I'll show you how quicksort works. Okay, let's continue now. So now that we have the partition procedure and we have the sort of overall view of quicksort, remember the view of quicksort was this. Now we pick we pick a pivot, we partition, and then we recursively sort L and R. We can convert this into code, without too much difficulty now. So the way we run this is we do quicksort on the array A. Again, n is the length of A, and so step 1 is if n is less than or equal to 1, just return A, or actually you don't even, in this case it's void. It's a void method, it's just going to return. Otherwise what you do is in place partition. So we'll partition, and in this case we'll partition A using A0 as the pivot, and then we'll get an array that looks like this. So we'll do quicksort of L and quicksort of R. And so again, L is equal to A going from 0 up to just before the pivot, and R is equal to A going from just after the pivot going up to n minus 1. Does this make sense, right? So you don't want to actually include the pivot itself because you don't need to. Okay? So you go everything up to the pivot, then everything after the pivot. You have to ignore the pivot because otherwise you can end up in an infinite loop. If L or R were empty, then you could have problems. So always ignore the pivot when you're making the recursive calls. So this is quicksort. Does this make sense? Okay, so at this point, what I have told you is quicksort and the partition procedure. And we've seen merge sort and the merge procedure, right? So hopefully you can kind of see the parallels between these, right? So this overall divide and conquer logic, it's making two recursive calls to a left part and a right part. And then there is some place where the real work happens, which is the merge and the partition. Yes?
So in the quicksort, we are passing the whole array, but this could be done with like the 2 pointers, like marking.
Yeah, exactly. You'll see that you could technically pass everything by reference, right? You just need, so that's why there's no extra memory allocated. Yeah. What do you mean?
So, like,
I see what you mean. Yeah, if you were to do it with pointers, then probably partition would take 2 pointers in, and then would just do it within that, right? So you have to be, yeah. But if you're passing by reference and the OS figured out like everything, then it would be fine for you, which it could in some cases, right? Like if you're doing C, an array is just a pointer. So if you send a pointer, it's the same thing as sending the array as long as you remember the length, right? So you can always do it with just sending 2 pointers, okay? But I want to sort of write it in this way so that you see these parallels here, right? Quicksort of L is merge sort of L. Quicksort of R, you do merge sort of R. And in merge sort, after you sort, then you merge. And in quicksort, the nice thing is it's automatically sorted once you call quicksort because you've already done the partition before it. Yes?
So in the merge sort, you were saying kind of if you are allocating the extra memory but you don't want to, you could like free it afterwards. Would you free the left
You could, but even then, when you call merge, extra memory is allocated during the merge step. So actually, it's not the memory that's created here that's the problem. It's the merge itself requires memory.
Isn't that what you're like returning to that LR? So reference is the same?
It is, but imagine, look at the top level call. That has to allocate that extra memory at that step. Even if the memory in the children calls was freed, there's still extra memory allocated at that very top call. Whereas there's no extra memory allocated over here because you're all doing it just within the array. Yeah, you'd have to, yeah, but the merge would actually only be called after these procedures return. I'm just saying that even if you look at the very first call, once these are completed, even if all of this was in place, it's still going to have to create a new array just to merge those two things. So there's no saving that. Okay, so, but does this make sense? So the reason I put this here is what I want you to remember, and I repeat, is you need to know the merge procedure and the partition procedure because these things appear quite a bit. Okay, these tricks of using pointers and marching those pointers in this way appears quite a bit. Now the question is, how do we argue about the running time of these, which is not as easy. Quicksort is actually, well, quicksort is like is a can of worms. So let's leave quicksort for a while, and let's go back to mergesort. To analyze the running time of mergesort, you need a mathematical technique called a recurrence. So it's a bit complicated in the sense of there's a new mathematical method that you need. So the way that I'm going to sort of, let me first write something down. Here I'll say the running time of the steps other than, now you can. The running time of the steps other than recursive calls. There. Is O of n. Right? This is important, right? So what this is saying is, if I look at all the steps other than the recursive calls, like this just runs in constant time. This, with pointers just runs in constant time. And this part runs in O of n time. So I'm going to write down that running time at the beginning. I'll say this is O of 1. And this is O of n, or O of 1. Let's just say it's O of 1 because you could do it with pointers. And this is O of n, step 5. Okay? All right, so how are we going to actually approach this problem? So let me define T of n is the worst case running time of mergesort on an input of length n. Question: what is the running time of step 3? Step 3 is a recursive call. Do I say it's O of n? Oh, sorry, blue. Do I say it's T of n? Or do I say it's T of n over 2? Right? So what is it? So I'll give you a few minutes to think about it. Okay, so what is the running time of step 3? That's right. It's T of n over 2, almost by definition. That's what I defined T of n to be. So the running time of step 3, I can write this as T of n over 2. And the running time of step 4, I can write it as T of n over 2. Sorry for the margins being messed up here. Right? So first step is O of 1. Second step is basically O of 1. Third step is T of n over 2. Fourth step is T of n over 2. The fifth step is O of n. Okay? Now the question is, what is, so technically an upper bound? An upper bound on the running time of merge sort on input of length n. Is it T of n over 2 plus O of n? Is it 2T of n over 2 plus O of n? Or is it 2T of n over 2 plus O of 1? So which of these is correct? What is an upper bound on the running time of merge sort on input of length n? A question?
Can you explain why step 3 and 4 are T of n over 2?
Sorry, okay, yes. So T of n is the worst case running time of merge sort on an input of length n. So it's like, I want to figure out what T of n is. So just like, in algebra, you define something as a variable, and then you write some equations to solve for that variable. Here, we're going to write an equation on a function and solve for the function. Right? The function is itself the variable, or technically an upper bound on the function is a variable. So this is like our variable. We don't know what this is. But if you look at L and R have a length of half of n over 2. Hence, the running time of this is T of n over 2, whatever that thing is. Maybe I should have said this earlier. R is also half of that, right? So I should have said this. Sorry, my apologies. So L and R are of length n over 2. So the running time is T of n over 2, and we're trying to solve for this T of n. Yes? We'll get there. We'll get there. First, answer this question. So what is the answer for this question? Like, what is an upper bound on the running time of merge sort? Yeah, it's blue, right? Because you see that there are two T of n over 2's here. Merge sort is called twice. So this is, what we get is T of n is at most 2 times T of n over 2 plus O of 1. And T of 1 is just O of 1. Like, this is like a base case. So the way to think about it is this 2 is the number of recursive calls. This 2 here is the size of input in the recursive call. Not the 2, but technically the n over 2. So the 2 is like the factor reduction. Your input is becoming smaller. And this part here is the time for the merge. Okay? So sorry, this is a bit messy, but now what we have is we have this funny kind of equation. It's like we're doing algebra over functions, right? So the unknown is an entire function, and the function satisfies these properties. So you have to solve this. This thing that I've written here is called a recurrence. And so there is basically a mathematical theory on how you solve recurrences. This is called a recurrence. And anytime you're doing some kind of recursion, the running time is often a recurrence. So even when you do binary search, there's a recurrence or binary search, although I didn't write it out that way. But if you think about it, it's like T of n is at most T of n over 2 plus O of 1. That's like another recurrence that comes up. So what we need to do is to solve this recurrence. And when you solve this recurrence, you essentially can solve this to get n log n. Okay? So you can solve this to get O of n log n. So you can solve this to get the T of n is O of n log n. Usually I do this in class, but I'm running out of time today. And so I might have to forego it. Maybe I can come back to it later on in the course when I get time. But the point is, in 102, you'll see more about recurrences and how to solve them. But this is how you approach the running time of Mergesort. With Quicksort, it's much more complicated. So actually in Quicksort, you pick the pivot at random. And so what you have is you actually have something called a randomized recurrence. So you have to do both probability and the algebra together. But you can work it all out. And then you get that Quicksort also runs in n log n. Yes? No, the T of n over 2 comes because this recursive call is to an array whose size is half.
So if we were doing something with the algorithm would just be like O of 1, would we still use T of n over 2?
Yes, okay, good question. So if magically I could get this to be O of 1, then you would still have this, but this part would be O of 1. And you get a new recurrence. And it turns out the solution for that recurrence is O of n. It's not obvious, but you can solve it, and you get O of n. And if this was O of n square, then it turns out this is just O of n square. So like, there's some math that you need to do. Depending on what this function is and what these constants are, there's a formula that tells you what this is going to be. Right? And yes? It's n over 2, which is the size of the input. 2 is like the fraction reduction. So actually, it's the whole n over 2 is the size of the input. But this inequality is a recurrence which you can solve using some sort of algebra. It's not very hard. Like this one, I can do it if I had like 15, 20 minutes. I could show you how to solve it. Okay, but it's not as important that you know it. All right? Okay, so I wanted to sort of take a few minutes to tell you about what I want to do next week. Because I've sort of covered, okay, at this stage, I think I've covered, again, all basic data structures, and I've covered sorting, partition, and merge, right? These are sort of the basic things that you need to know. Now, the next week and maybe the next couple of weeks is about how do you apply that knowledge to solve problems. Okay? So what I think you need to now sort of learn, or the next stage, is what I call the design and analysis of algorithms. So here's what you need to be able to do, which is given an algorithmic problem, you have to write pseudocode. You have to write clear pseudocode for an algorithm solving the problem. Perform a runtime analysis using the big O notation. right? This is what test 4 and actually test 5 is also going to be about. Test 5 is on graphs. It's a more complicated set of questions. But the idea is I'll give you some problem, right? I'll describe some problem to you. Like I'll say, okay, so given a collection of numbers, find, I don't know, something like, find 3 numbers whose sum is x or something like that. And what you need to do is you need to write pseudocode the way that I write pseudocode. You can structure it wherever you want. I don't care if you make mistakes with pointers and arrays and indices, but your pseudocode has to be correct. And then you perform a runtime analysis using big O notation. And the way to do that, again, is I'm not going to give you anything as complicated as Mergesort, but the best thing is for every step you say, okay, this runs an O of 1, this runs an O of 1, this runs an O of n, so on and so forth. So you just write that down and say this is the runtime. If you have nested for loops, you'll say this runs an O of n squared. If you have a data structure, then... So I'll be doing many examples of that in the next week, where I'm going to give you a set of questions. Read over those questions. There are like 50 of them, right? So you will not be able to solve all of them in a day, or in a week, or even by the end of the quarter. But work on them for like the next few months, and look over them anytime you want to brush up your data structures and algorithms knowledge. And for every problem, you need to write pseudocode and perform runtime analysis. Okay? So there is sort of a structured way of doing this, which we'll talk about, which is always approaching a problem from brute force and then trying to improve brute force. Instead of trying to come up with a complicated solution, you come up with a simple solution using only arrays, and then you slowly start introducing data structures to improve that. Yeah? For all of them? No, that's hard because all of this is written, right? Someone has to read it and go over it. But often, like a lot of classic interview-style data structure or algorithms questions are of this form, where people might put you up on the board, give you a question and say, okay, how do you solve this? So you write some pseudocode and then you write a big O analysis, right? And so you need a lot of practice doing that with lots of different questions. Yes?
Sorry, this is a little off topic, but for the homework, are they due on Sunday at midnight, and are they due through Codio? Because I know you can't do.
Yeah, always.
Okay.
But there's no homework regarding this, though.
No.
There's a test. So the test for this is going to be written, right?